I'm going to get started. I know the whole class isn't here yet, but I'm assuming they'll show up as soon as they can. I checked my email. I don't see anybody sending notes saying that they can't get in, so I assume that some people are just running a little late today. I want to apologize again that I didn't get there on time for our office hours yesterday. I usually log in, a half hour before our session is supposed to start, and I didn't get in for more than an hour. I don't know what the problem was. It just started working. I rebooted my system a couple times. I just don't know what was going on, but it seems to be fine today. I also had difficulty last night my time, logging into the SEU website at all. It wouldn't let me in, and don't know what the problem was there. I had been told that the SEU website and Blackboard was more stable now than it used to be, but I still seem to be having difficulty getting in at times. It would have been, really early in the morning your time, so you may not have noticed, but it is frustrating when you're trying to get something done and you can't get into the system. So again, I apologize for yesterday. Hopefully all of you received the midterm study guide, and I was very happy to receive that as well, and I'm glad I was able to get answers to the questions as to whether what was in the study guide was all that was on the exam, and as you saw from my notes, that's what I was told, that the study guide should help you focus on what's important for the exam. So hopefully if you review all the materials in the study guide, you will do fairly well on the exam. It's strange for me as an instructor, as a professor, not making the exam and the study guide for my students and not knowing what's on it. I still haven't seen the exam to see exactly what that looks like. It's just an unusual situation for me as well. So I try to get you all the information I can, but sometimes I just simply don't have the information. So if you got the study guide, I wanted to make sure that you were aware of the differences. I know some of you had been looking at a different version of the textbook. I don't know if everyone is now using the correct version, which is the International Student version with the brown cover. The study guide references those chapters from the International version. If you're using the blue cover version, the chapter numbers are different. So this table here just shows you some of the differences that I know of between the two textbooks. Okay, so your study guide again is referencing the chapter numbers that are in the brown International Student version of the book. So this week we're going to be talking about file systems and file system implementation, and we have a number of learning objectives for this week. I won't have the time to go through all of this. I want to make sure that I do cover the things that were highlighted in your study guide to make sure that you understand those before the midterm. And then if you have questions on the other sections that you read in your book, you can always email me or post something on the discussion board. Also, in the interest of time, I'm not going to go over your homework assignment from last week. I will be doing that in the future. Same thing with your programming assignment. I'll get all that back to you. But for this week, I'd like to just focus on the information that's on file systems and file system implementation, as well as any questions you might have once you looked at the study guide. Siham, you said yes, please. What are you asking for or agreeing with? Okay, focus on the midterm. Okay. So this week's topic, we're talking about files, and files are a logical storage unit mapped by the operating system onto non-volatile physical storage. So this is, you save things out on disk because you don't want them to go away. So you want it to be non-volatile physical storage. The concept of a file, though, is kind of an artificial concept, an abstract data type, they call it, because it's kind of how we think of a file. It may not match what's actually out on disk. So we think of files in a certain way, but the operating system is really just worried about getting those file blocks from the physical disk space into memory and vice versa. Another definition of a file is a named collection of related information recorded on secondary storage. So when we're looking at files, you might say, oh, I have a file of student records, or I have a file of my financial records, or that type of thing. All the records, all the information in that file is related, and that's how we kind of group information together so that it makes sense for us. Another type of file, another way to look at files is that files contain either programs or data. And we've seen this, we've had a .java file that's a source file, or we've had a .class file, which is the executable file that the Java virtual machine uses. Or if you were writing C code, you would have an a.out file or whatever .out file. That would be your executable file. So all those things are programs, but then there's also the data. There's the data that is in the program, the data that the files use, or the programs use, I should say. So you're kind of familiar with these different file types. One of the things that I saw in the study guide is that it said executable file was one of the topics, and really an executable file is just the code sections that the loader can bring into memory and execute. And we talked about that some when we talked about linking and loading and bringing files in, and how a process had to be in memory in order to execute. And so the executable file is kind of like the process out on secondary storage. Another topic that's in the study guide is the file attributes. And one thing I liked about looking at chapters 10 and 11 is that we're familiar with a lot of this stuff already because we use files all the time. So you've probably looked at what files you have on your hard drive, and you know that there's a file name, and the file name is really the only thing that's kept in human-readable form. There are identifiers. Each file has an identifier that kind of numbers it for the operating system. And when you look at a directory, or in Windows they often call them folders, you can see your different file names. You may not see the identifiers. But the identifier is what's used to locate the other attributes. So if you ever look at something in your file system on Windows or on Linux, you can do different commands to look at the file system, and it can give you as little or as much information as you want. It could just give you the file name of all the files in the folder, or it can give you the amount of storage that they use. It could say when it was last accessed, who owns it, and so forth. So those are some of the other attributes that you might see when you look at a listing of your files. So there's the type, and you've seen, .jpg might be a JPEG, or .exe will be an executable, .doc will be a word processing file, and so forth. And those are the types. They're also called the extensions for the file. Of course, it has to know where to find each of these files on disk, so there's a location. And that's really a pointer to your hard drive or wherever the file is located. We have the size of the file, and that could be in bytes, in words, in blocks, however the operating system displays it to you. So we have how many, how big is the file. The protection is who can read, write, or execute the file. Okay, who has those permissions for a file? And you'll see that sometimes, I've done things where I've been working on a file and then I try to send it to one of my kids in a message, but I never really got out of the word processor. So the word processor has it open. I can't send it because it's still open. That's one sort of protection. Another sort of protection is there are certain operating system files and so forth that I can't read or write to because the system protects it. Also, who can run certain files. That's another way that the system protects itself from files being run that someone's not supposed to run. On a multi-user system, of course, there's always protection between the users. We don't want users accessing each other's files unless they've been given explicit permission. Okay, there's also the time, date, and user identification. Usually this information is kept for when a file was created, when it was last modified, and when it was last used. And again, this is used for protection and security. It's also used for when you're monitoring who's using the files. Muna, you had a question? It's prayer time now. Isn't our class being held at the same time it always is? Did you always have prayer time at this time? I wasn't aware of that. Okay. How long is prayer time? Your time is moving. Okay. If you need to go, why don't you go? And I'm going to continue here, and you can come back and look at the slides in the recording if there's anything important that you've missed. Okay, so just drop out if you need to, and then come back. We really have a lot that I want to cover today, so. Hopefully, I'm going to be talking about the file operations, which you're probably already aware of because you've done files in your programming assignments or whatever. Okay? Okay, so if you need to go pray, just do that, and then just join us as soon as you can. As far as the file operations, there are a number of things that you're going to want to do with a file. First is create a file, and in order to create a file, space in the file system must be found for the file, and then an entry for that file is made in the directory because you want to keep track of any files that you've created. So that's the create operation. The write operation, when you do a system call for a write, the system call includes the file name and the information that needs to be written. So again, the directory has to find the file's location and then write to that location. Okay, and sometimes the write operation includes a create, like if you're doing a write in a certain programming language, it might include the create if the create hasn't already happened, but often that's done with an open. When you go to open a file, it may create it, and then you write to it. So when you're writing to a file, the system uses a write pointer to keep track of the location in the file where the next write should occur. So the operating system is responsible for making sure that you're writing in the right location on disk, and also that you're not overwriting other information that's out on disk. When you do a read Again, the system call specifies the name of the file to be read and the position where the data should be copied in memory. So again, it has the file name, it searches the directory to find the location of the file, and then it uses a read pointer to keep track of where the next information will be read from the file, read from disk into memory. Since you need to use a pointer for both reading and writing, often a single current file position pointer is used for both. Okay, so the file position pointer might be used to say here's where we write to the file, or it may be used to say here's where we read from a file out on disk. Some other operations are the seek operation, and this is where you're repositioning that current file position pointer to a certain location in a given file. So with the reposition or the seek, again, you need to search the directory to find the file that you need to that you want to reposition the file pointer for, and then you use the seek to go to that file position. Delete is another operation that you may want to do on files. And again, with delete, the directory search to find the file's location, and then the file space is released and the directory entry is erased. So when you create a file, the file space is allocated and the directory entry is created. When you delete a file, the file space is released and the directory entry is erased. Excuse me. And then finally, we have here a truncate. And what a truncate does is it keeps the directory entry, so it doesn't have to recreate anything in the directory, but it modifies that directory entry to say, I'm starting over at the beginning of my file, and I'm releasing any file space that file was holding on disk. Okay, so that's what a truncate does. A lot of times this is used when you're actually rewriting a file. You've already read it in, you've made some modifications to the information or the data, and you want to write it back out kind of as a new file. Rather than creating a new file, you can do a truncate to reuse the directory entry and just reset the file length to 0, and then go ahead and start writing to that file. So you can see in all these cases, we're opening and closing, or we're searching for the file location repeatedly. And so that we don't have to do that over and over again, usually in our programs, we are opening and closing files. When you open a file, it puts an entry in what's called the open file table. And the open file table keeps information about all the open files, and it keeps a table per process and also a system-wide table of all the files that are open on the system. And that's where it'll track the current file position pointer, how many processes have this file open, where the file is located on the disk, and also what access rights there are to this file, who has read permission, who has write permission, who has execute permission. Okay, so all that is kept in a file for each file that's open, and that's why your languages like Java, like C, like COBOL, whatever languages you know, they will open files and then close them when they're done, because that's what's managing this open file table. Okay, so again, we use the file pointer for the last read or write location. This would be per process for every process that has the file open. We use the file open count as a counter of the number of times the file is open, so that the operating system could keep track of how many different processes are opening the file, and then once all the processes have closed the file, it can release the open file table space. The disk location of the file, again, we want to cache this data access information so we don't have to keep looking through the directory to find where the file exists on disk. And then, of course, the access rights, as I said, is the per process access mode information saying who can read, write, and execute a file. Okay, another question that was in your study guide was about the file types or the file extension. The file extension is usually what's used to indicate the file type. And depending on the file type, that affects what type of operations can be done on a file. Some of the file types are, the operations are handled by the operating system. Other file types are handled by different application programs. So for instance, an executable file, which might be an exe file or a com file or a bin file, or it may have no extension, that means that that's a ready-to-run machine language program. So the operating system would take care of handling operations on that file, because those are the files that are our processes that are going to be loaded into memory. Okay, object files or .o files are often compiled programs, but they haven't been linked. Source code files you're familiar with because you've done Java, batch files. Back in the old days of Microsoft, before it was, when it was Microsoft DOS or MS-DOS, before they had the later versions of the Windows, you used a BAT file to help control certain things on your system. Text files you're aware of, the word processing files, and so on. So you know, I think you understand what a file extension is used for, because when you look at your folders and you look at what files are in those folders, you usually look at the extension to see, oh, well, what kind of file is this? And that's exactly what the operating system does as well with the file extension. Depending on the file extension, though, it may also tell the operating system something about the structure of the file. Same thing with application programs. When an application program like Photoshop, for example, sees something that has a file extension of JPG for a JPEG file, it's assuming that file will be formatted in a certain way. That file will be structured in a certain way. And so the file extension tells you the file type, gives some ideas about how this file can be manipulated, and also might indicate the structure of the file as well. In which question am I? You're talking about in the study guide. I didn't really write all that down. But there was something that talked about file attributes, and the type is a file attribute as well as executable files. Okay, so that's numbers 17 and 18. And I'm not just going through this in direct order. I'm kind of covering the information from week 7 that I know is on the exam according to the study guide. Okay? Okay, so to understand some of the other things in the chapter, yes, I'm in week 7, and I'm going over specifically the things that are in the study guide for week 7, plus a little background information that you need in order to understand some of the later topics. So when we talk about file structure, we're talking about the logical records that are the programmer's view of the data. And these are actually mapped to the physical records that are dependent on the size of a sector on a disk. So files on disk are allocated in terms of blocks, and all your basic I/O is done in blocks. The logical record size doesn't usually match the physical record size. Multiple logical records, or how you as a programmer or a user think of the records, may be packed into a single block or physical disk space. And what this means is that you may have internal fragmentation because there will be unused or wasted space because you're packing logical records into blocks. And so if we have records that are each 100 bytes long, and we have blocks that are 512 bytes long, there's always going to be 12 bytes that are unused at the end of each physical block. So this little bit of wasted space is called internal fragmentation. And that's important to know because as we look at some of these access methods and some of the ways that we try to make our disk access more efficient, we look at both internal and external fragmentation. So when we talk about records, we're usually talking about logical records, which is how programmers view the data. And then we have blocks, which are the physical records, and that's what we're doing for I/O. The way we access the files is, there's a number of ways, but the two main ones are sequential access and direct access, or it's also called relative access. So with sequential access, information is processed in order, one record after the other. So we read the next record, we write the next record, we can reset to the beginning of the file, or we can skip so many records forward and backward in a file. But basically, we're reading the records one right after the other. So if we look at, having a block where we have multiple logical records in a block, you can see how, since we're reading them sequentially, one after the other, it's good to bring a whole block into memory because we read record 1, then record 2, then record 3, then record 4, then record 5. And so we bring, 5 records in. In this example, of course, your record size and block sizes will vary. But we bring, 5 records in at once with a block and do the reading when we use sequential access. For relative access, we can access any block in the file kind of randomly. So we say read, block N, or read record N, or write record N as we go through our file. We're not actually accessing one record after the other in sequential order. We're kind of jumping around in the file. So you can kind of think of this, the way I kind of think of it is if you have an iPod and sometimes you're listening to music and you're just listening to one song right after the other the way the artist put it on the album. That's sequential access. Another thing you might do is do like my iPod might have a shuffle kind of function on it. So that would be more like a random access or a direct access where I'm accessing the different songs in random order. Okay, so you see the difference between the two. Usually you use direct access files when you want immediate access to data and things like a database where you don't want to read from the beginning of the file to the end. Instead, you want to take a record from the middle of the file and then one from the beginning of the file and then one from the end of the file, and you're jumping all around in that file. We also have indexed access methods where an index is built on top of a direct access file or a sequential access file, and the index is kept in memory, and the index will help you find the location of the data that you want to manipulate. So usually with an index file, the index is created and searched to find a record, and then that has a pointer to access the record directly out on disk. So if the index is too large, we might actually have to have the index out on disk, and then we can have indexes of indexes and so forth. But it's all really just meant to help you get to certain records in a file more efficiently, especially because you may not want to always access the files from the beginning to the end. So sequential access doesn't work, and you also are going to be reading in whole blocks from here and there, and so you want to be aware of how much wasted space you have as far as fragmentation on the disk. With certain access methods, having continuous allocation is good. With others, it's not as good, and we'll talk about that in a little while. So any questions on what we've covered so far? I know I'm going kind of quickly because I want to get through the week 7 information that's on the exam. Okay, you have 2 homework questions that are due after the midterm. Question 10.6, and it says if you know that an application is going to access a file in a sequential manner, how would you exploit this information? And then the next question is what kind of application would benefit from a random access file if you're using an indexed file and accessing it randomly. So you're just kind of thinking about, what kinds of things would you be doing in a program when you would want to access something sequentially or access it randomly. The deadline for the homework isn't until the week after, until the start of week 9, which is after your finals. But I wanted to put these up here because you'll be working on these this week when we don't have class in week 8. Okay. So yeah, I moved that till after your midterms, your assignments due, but I want you to be aware of what the assignment is since it relates to what we're talking about this week. Okay, for the file system, file systems are often created as a layered kind of architecture where you have your devices at the very bottom, then you have some control functionality, then your basic file system, followed by your file organization. On top of that, you would have your logical file system, and then that's what your application programs access. So you're actually accessing the physical storage device all the way down at the bottom of this layer, but as a programmer, you're accessing things using the very top layer. And so you're actually going through all these different layers before the physical device is accessed to read the information that you want. So your basic file system has commands to the device driver, and when I'm talking about basic file system, I'm talking about this layer right here. We're not going to worry about the lower layers this week. We'll be talking about those after the midterm. But the basic file system issues generic commands to the device driver to read and write those physical blocks from disk. It's the basic file system that manages the memory buffers and the caches, and some of what's in your study guide is asking about a buffer cache. So a block is allocated in a memory buffer before the data is transferred from disk, and the buffer manager finds and frees this buffer memory. Okay. Caches are used to hold the file system metadata to improve the performance. Okay, so your basic file system is managing both these buffers and the cache. Okay, and the cache is where certain things are held so that your file system will perform more efficiently, will perform faster. The file organization module, which is on top of the basic file system, is translating the logical block addresses to the physical block addresses, and it also manages free space. That should say free space management, not manage. It includes the free space management. It tracks what blocks haven't been allocated, and it provides unallocated blocks to the file organization module when they're needed. Okay, so the free space manager, that's what I should say, the free space manager tracks the unallocated blocks and provides unallocated blocks to the file organization module when needed, which again, these get passed up through the layers till eventually the application program knows it can write to a certain place on the file. Okay, so in your study guide, it does talk about free space management, and I'll talk a little bit more about this in a few minutes. Okay, the logical file system, which is the next level up, that's what contains the file system structure that we're kind of used to looking at, the directory structure. All that file system metadata is kept in the logical file system. The directory structure is managed. And the files themselves are managed using file control blocks, or FCBs, that contain information about the file, including who owns it, what permissions are on the file, and where that file is located. And we already talked a lot about how we need to the operating system needs to be able to find these files out on disk. And it's also responsible for file protection, making sure that users aren't overwriting files that aren't theirs. Okay, and this just gives you a couple pictures that you can look at for the file system implementation of kind of how we see the files when we open them or when we read them, and then the different structures, the directory structure, the open file tables, and then the file control blocks and so forth that are used to actually get to those files on your secondary storage. Okay, so this is a nice picture to keep in mind as you're thinking about the file systems. Now, out on the disk itself, there are partitions, and again, this is something else that's in your study guide. It's important to realize that disks are often configured by dividing the entire disk space into multiple partitions. And you may have looked at the partitions on your disk space when you had a disk crash, when you had to reload your operating system, when you were trying to figure out why your system wasn't running quickly, because you have all this fragmentation, and you might have looked at the partitions on your disk. But basically, the disk space is divided into multiple partitions. A raw partition is used for the swap space, and we talked about swapping. It's used sometimes to hold some database data, or it's used to hold boot information. Okay? A raw partition is a partition that doesn't have a file system in it. It's kind of free, kind of a free format of the data, and it's used for very, very specific purposes. Swap space, which is just general free space, database data, boot information, that's what's in a raw partition. A cooked partition, on the other hand, contains a file system. Okay? So that's one of the things that's in your study guide is talking about raw and cooked partitions. Okay, so usually you're not accessing anything that's in a raw partition. You're accessing things in a cooked partition, which is where your file system is. And that's why sometimes if your boot partition, for example, gets messed up, you can't use your system anymore, because the operating system is depending on that boot sector to actually load itself, to load the operating system into memory. So the raw partition would hold the boot, would be the boot sectors. The cooked partition would be the file system when you're thinking about an operating system. There's something called a root partition, and that's what holds the operating system kernel and the system files that get loaded into memory. So it's often in a special place on the disk. Now, when we're allocating these blocks, we We can allocate them using contiguous allocation. And again, your study guide also talks about the different allocation schemes. Each file occupies a set of contiguous blocks on the disk, and often this is the best performance. If you can use contiguous allocation for a file, because remember you're bringing in blocks which have multiple logical records in them, and if it doesn't have to move the disk head as it's reading the next block, it makes your disk drive faster. Okay, so if you can store an entire file as a contiguous set of blocks, one block right after the other out on disk, that will give you the best performance. So your directory entries then will contain the address or the starting block number of the file and the number of blocks that are contained in the file. The problem with this scheme is that you have to find a space large enough to hold the entire file. You have to know the file size, and you can have external fragmentation. And this is similar to fragmentation when we talked about it in memory. What happens is you're allocating contiguous blocks on disk, but it's allocating them in these partitions, and there may be some free space that isn't being used in a partition. And so, that's your external fragmentation. Pieces of free space that are scattered all around on your disk that it couldn't use. Okay, because you allocated a whole block, but or a whole bunch of contiguous blocks, I should say, but the file is only using some of them. Okay, and so there's this free space on disk. Now, when your file or disk drive is fragmented, usually what you have to do is, not use your system and do something called compaction. And you may have compacted your disk drive in the past to give you more free space. So this just kind of gives you a picture of what contiguous allocation looks like. There are different files, count, tr, mail, list, and so forth are all names of the files. We have the starting block and the length. So file count starts at block 0 and is 2 blocks. So you can see here count is these 2 blocks out on disk. Then, file tr is these 3 blocks on disk, and so forth. So you can see the files are scattered all around, but they're using certain blocks out on your disk. And even though the files themselves may be here, there, and everywhere on the disk, the actual records within those files are stored in contiguous blocks on the hard drive. Another type of allocation is extent-based allocation. So this is kind of like the contiguous file scheme, except that the disk blocks are allocated in extents. And so rather than having to allocate one big contiguous space of blocks on your hard drive, it allocates extents, and each extent is contiguous, but you can have multiple extents that are all over on your disk drive. So a contiguous disk space or an extent is allocated for the initial file, and then more extents are added as the file grows. And each extent points to the next one. And this is kind of what we saw with some of the dynamic paging schemes that we looked at for memory. This is the same idea on disk, where files are allocated the disk space, a small amount at first, and then more extents are added as they're needed. And then we have linked allocation, where each file is a linked list of blocks. The blocks may be anywhere on disk, and each block contains a pointer to the next block. With linked allocation, we don't have external fragmentation or need to compact our hard drive. We don't have to allocate all the blocks at once, and we simply grow the file by adding a new block. The problem is, with linked allocation, it only works well for sequential access, because if we want to locate a block randomly, it can take many IOs and disk seeks to find the right block on disk. And then the pointers to go from block to block will take space, and they can get broken. If a file pointer gets broken inside a file, you've lost any accessibility you had to the remainder of that file on disk. So it is a reliability issue. But linked allocation looks more like this. We might have a file called Jeep, and it starts at block 9. And so we look, here we have block 9. And then block 9 might have a pointer to block 16, which might have a pointer to block 1, which might have a pointer to block 10, which then has a pointer to block 25, which is the end of the file. So the different blocks for a specific file are no longer contiguous. They're all over on the hard drive, and the system has to follow all these file pointers when it's accessing the file sequentially to find the next records in the file, or to find the next block for that file. Now there's a variation of a linked allocation scheme called FAT, and what it does is it uses the block numbers as an index into a file allocation table that's in the beginning of the volume on your disk. So the table entry contains the block number of the next block in the file. So we index, we know what block number we're looking for, we look into this table, the table points us to the next block in the file, and so forth, and it's very much like a linked list, except this table that's created can be stored in memory while you're using that file, so it's cacheable. So it can be accessed very, very quickly rather than always going out to the hard drive whenever you need a new block. You know just to go to this FAT or file allocation table to find the next block. And then here's a picture of that, where you can see that we have a start block, but now this table, rather than being out on disk, is simply in memory, so you can access it more quickly than you could with the linked allocation table. Indexed allocation is the last allocation method that we'll talk about, and with indexed allocation, pointers to the blocks are stored in an index block, which is an array of block addresses. So again, this is similar to paging, and we can get to different blocks directly and have no external fragmentation, because each block is just being pointed to in this index. Now we still may have some wasted space because the entire index block has to be allocated. And remember, a block is based on the sector size on your disk. So an entire block has to be allocated, even if the index only has a few blocks that it needs to point to on disk. So we might have this big space allocated for the index block, and then it only has a few entries in the actual table. And then the other problem is that if the index is too small, we can use a linked scheme, a multi-level index, or a combined scheme to create additional pointers. Kind of like we saw when we looked at index paging. Here we're going to have an index to an index, or an index to a linked list, or whatever, to get us to those additional blocks if we allocated our initial table to be too small. Still, there's a performance problem versus contiguous allocation, because the blocks are distributed on the physical disk, and so you have a lot of head movement and the actual hard drive rotating as it's trying to find these different files on the disk. And again, here's a picture of what indexed allocation looks like. The only thing we have in memory is this index block, which takes us to this block, which is just a block of other pointers to other blocks on the hard drive. Okay, sometimes this index block can be read in, kept in memory, kept on disk, and then that will give you more efficient access of your files. So any questions on these different allocation methods? I know that this is on your exam. And you also have a question about it, 11.17, that's talking about logical and physical block sizes, and how is it done for the 3 allocation strategies. How does it work for contiguous allocation, linked allocation, and indexed allocation? And so you just have to kind of think about these different ways to do it, and then how are these different things accomplished in the system. So that's a homework assignment. Again, that's not due until the 23rd, but I wanted to make sure that you knew what the problem was that you needed to do. Another question that's going to be on the midterm does have to do with free space management. The system has to know what's available on disk and what has been freed. So the file system maintains a free space list to keep track of what clusters or blocks are available. The simplest of these is to use a bit vector or a bitmap where the free blocks have a value of 1 and an allocated block has a value of 0. So it's very small, very simple, very efficient, and you just keep this entire bit vector in main memory for every block that you have out on your hard drive. Okay. Another free space management technique is a free list, and with a free list, it links all the free blocks together. And the pointer to the first block is cached in memory. And so when you need to get a free block, it simply looks to that first block that's cached in memory. And in this case, it would say, oh, my first free block is block number 2. And so you just go out to disk, you get that, you can use that free block. You hardly ever need to traverse this entire list from 2 to 3 to 4 to 5 to 8 to 9 to 10 to 11 and so forth. Because usually what you're looking for is where's a free block. When blocks get freed up too, they're just added to that free list. Okay, and they could be added at the head or at the tail. But either way, it's very simple for a linked list structure or a doubly linked list structure to be used to find the different blocks on your file. What's hard, though, is if you want to have a bunch of contiguous blocks so that you can read a sequential file more efficiently, then this linked list doesn't work that well, because as you can see in the picture here, these blocks can be all over your disk space, and if you needed something to allocate, let's say a 6-block to store 6 blocks of information, if you picked block 2 as your first free block, that would only give you 4 contiguous blocks, when it would then have to go out and find more contiguous blocks out on disk, and you actually have other blocks in between. So it's hard with this scheme to find contiguous blocks on your hard drive if that's what you want. There are a few other free space management techniques. One is grouping, where it stores the addresses of the next free blocks in a free block. And so that's one way to do it. And so you just pull in the free block, and once you use up all the free blocks that are located in that free block, you'd pull in the next free block, and so forth. So you're pulling in a block of free blocks is what you're really doing in the grouping scheme. Another scheme is counting, and I believe this is asked about on our midterm. And this takes advantage of the fact that free space is often contiguously used and freed when you're doing contiguous allocation, expense, and clustering. So each entry in the free space list has the address of the first free block and the number of free blocks that follow. So you have a bigger entry in your structure, but your list is shorter. So instead of having an entry for each block of free space, you only have an entry for the first block, and then you put the number of free blocks that follow. So I might say I have block 2, and then there are 7 free blocks after that. Okay, so that the system knows. It counts how many free blocks follow the block that's referenced in the entry, in the free space list. Okay? Does that make sense? Okay, the other thing that we need to be worried about here is free space management. And the efficiency really depends on the disk allocation and the directory algorithms that are being used, and the types of data that's kept in the directory for each file. So things like the pointer sizes, the data structures, whether you're doing dynamic or static allocation of some of your data structures, whether you have fixed size data structures or variable size, that's all going to affect the efficiency. And your study guide implies that there's a question about the efficiency and how the performance can be improved using cache. Disk controllers usually have an onboard cache that's large enough to store entire tracks at a time. Okay, so the operating system, or the disk controller, I should say, will bring in an entire track from disk at a time. And then the operating system also might use a buffer cache, which is a separate section of main memory for blocks that are frequently being used. The operating system also uses a page cache that uses virtual memory techniques that we talked about last week to cache the file data as pages rather than blocks. Okay, so a buffer cache caches blocks, a page cache caches pages. So normal routine I/O uses a buffer cache, and memory mapped I/O uses a page cache. And what happens is we end up with something that looks like this. We have memory mapped I/O using the page cache, but everything has to pull things into a buffer from disk. So we end up with a buffer cache as well, and we end up with some information that gets cached twice. It gets cached in the buffer cache as well as in the page cache. And I know we're close to running out of time, so if you need to leave, I do understand, and I'll just finish up this last topic because I believe it's on your midterm exam. So what some systems do is they use a unified buffer cache where they only have one buffer cache, and it's used both as the page cache and the file cache for ordinary I/O. Okay, so that avoids that double buffering type of problem, or double caching, I should say, type of problem. Okay, so that a unified buffer cache will help avoid the double caching. Both the memory mapping and the read and writes will use system calls, and they'll use the same page cache. And it also allows the virtual memory system in the operating system to manage file system data. Now, how do you manage the buffer cache, which is what we've been talking about, and this is where I get to, kind of what it asks about on your midterm. It's actually difficult to choose an algorithm to manage a buffer cache. In other words, what blocks do you get rid of in a cache? How do you know that they're not going to be needed again right away? Intuitively, it seems that LRU would be a good algorithm for managing blocks or pages within a cache. And again, if you need to leave, I understand that. I do know you have other classes and other things going on, but I do want to continue to cover this, and you could jump to this point in the recording after you're done with your other class. So least recently used might be a good algorithm for managing blocks or pages in a cache. Okay, just that might be your first thought, because a block that we used a long time ago, chances are it's not going to be used again. But with a unified buffer cache, we have a problem. Sometimes some of the blocks or pages that are in the cache are from processes, not from the I/O. So we might have a problem if the unified buffer cache using an LRU algorithm tosses out a process page rather than a disk page when it wants to actually put disk information into the cache. Okay, so LRU might not be the best option there. You might need to use an algorithm that has priority paging so that the process pages, okay, and remember from last week, process pages are those pages that are the actual code that's being executed or run, and the process scheduler scheduled those pages, put those pages in memory, and they're being allocated to the CPU. We might want to use priority paging to give those process pages a higher priority than the I/O pages, okay? So that when you're reading a lot of stuff from disk, process pages that were brought in a long time ago won't be tossed out or replaced with your page replacement algorithm. Another option that you might look at when you're choosing a page replacement algorithm is to do something where a file system page would not be allowed to force out a process page and vice versa. So you can modify your algorithm so that file pages will only force out other file pages, and process pages will only force out process pages. Another way to optimize your buffer cache is by using different page replacement algorithms depending on the file type. And so what we might have here is having a sequential file, which we wouldn't want to use LRU for our page replacement, because it's usually with a sequential file, you read a record, and then once you read that record, you're done with it. You're moving on to the next one. So why not let the file system just replace that most recently used file block rather than the least recently used? Okay, so sometimes you can make your file system more efficient by actually using a different algorithm. And there are two algorithms that your book mentions. One is the free behind algorithm, and the other is the read ahead. The free behind algorithm removes the page from the buffer as soon as the next page is requested. So that makes sense, because if I request page 1, and then I move on, I'm reading my file sequentially, I read all the records in that first page, and then I want to read whatever records are in page 2, I'm done with page 1. I've already moved my current file pointer to be past those pages, and so now I can go out and get the next page and actually replace the page 1, that I first read into memory. Okay, so you can see how that would be more efficient, because you're just reusing the block that you just used or you just read. Another way to make a page replacement algorithm more efficient is to do read-aheads. And again, remember with sequential processing, it's reading the file from the beginning to the end. And so what you might want to do is when it goes out to read from the disk, have it read a lot of pages and cache those in memory. So then when it needs to get the next page, it's simply the next page in memory. So this is very efficient because you know with a sequential file you're always going to be reading or writing, of course, in sequential order. So your cache can be set up so that when it goes to do a read, rather than just reading, one block or one page, it reads a number of blocks or pages, because chances are the application program is going to need to go out and get those pages next. So that's one way of managing your buffer cache to make it more efficient, or there are two ways actually, the free behind and the read ahead, to make it more efficient for sequential file access as opposed to using something like the LRU page replacement algorithm to manage your buffer cache. Okay, so that was all that I saw in this week's material that it looked like was on your midterm exam. Of course, I've been told that more things may be on the final exam. I don't really know. Again, we're not going to worry about the final right now, but hopefully if you were able to follow, I know I had to go kind of quickly through this, if you're able to follow along, this kind of gives you the sections in your book that you can look at to understand those things having to do with the file system and the file system implementation that may potentially be on your midterm exam. Any questions either about this or anything else that's on the study guide, or anything I can help you with? Again, hopefully you'll find the study guide very helpful to let you narrow down what you need to study. I looked at the study guide, and I think what I've covered today covers a lot of the things. You're still going to want to read your book, but the things that were in Chapter 9 are, I'm sorry, not Chapter 9. My book is, I'm looking at the wrong version of the book. I have to remember which version you guys have. But we covered things like the raw and cooked partition, file extensions, internal fragmentation, the basic file operations, the using linked allocation of disk space, the counting approach to free disk space management, algorithms for managing your buffer cache, the file access methods, the file attributes, examples of executable files. Those were all the things that were in your study guide that were in this week's reading materials. Okay, so those are the things that you're going to find in chapters 10 and 11. Okay. Any questions? Okay, as you're doing your studying, if you're going through the study guide and find there are any things that you don't understand, please feel free to email me and I'll help you if I can. If not, good luck. I hope you all do very well on your exams. We won't be meeting again until week 9, okay? I'm going to be out of town, and I'll send you a note to remind you of this. I'm going to be out of town for a few days next week, so I'll still be checking my email, but I may not check it as often as I do when I'm at home. So I'll send you a note just to remind you before I leave. I'll be gone Thursday through Monday, the 20th through the 24th, but I will be available via email. Latifa, did you have a question? What's your question about the midterm? The midterm will cover the topics that are in your study guide. That's what I was told. I asked about that, and the midterm will cover those topics. Okay. So I was told that if you focus on the study guide, that will help you on the midterm. So that study guide, and then I think Muna actually sent something out where she provided some more information in the study guide from the chapters. I think she sent that out to the whole class as well as some other PowerPoint presentation that I didn't have a chance to look at, but I think it was a study guide that some professor not at SEU created for his or her class. So I think Muna actually sent you some additional information as well. Okay, but what I was told is that the study guide is what you should focus on for the midterm. I still haven't seen the midterm, so I can't guarantee it, but I could just tell you what I've been told. Okay? Any other questions? So check your email for these study guides, both the one that I sent you and the one that Muna sent. Okay, I'll be thinking about you a lot, and I wish you well on your exam, not only in this class, but in your other classes as well. And we won't be meeting again until office hours on the 25th or our class session on the 26th of March. Okay.